Welcome to this lesson on electric dipoles. Today, we'll be exploring the electric field intensity due to an electric dipole at a point on the axial line. First, let's understand what an electric dipole is. An electric dipole consists of two equal and opposite charges separated by a small distance. The positive charge has a value of plus q, and the negative charge has a value of negative q. The distance between these charges is denoted as 2a. Now, let's define the electric dipole moment. The electric dipole moment, denoted as P, is a vector quantity that points from the negative charge to the positive charge, and its magnitude is the product of the charge and the distance between them. Mathematically, P equals Q times 2a. Let's now focus on finding the electric field intensity at a point on the axial line. The axial line is the line that passes through both charges and extends beyond them. We'll consider a point P at a distance, or from the center of the dipole, along this axial line. Before we calculate the electric field at point P, we need to understand how each charge contributes to it. The electric field due to a point charge is given by Coulomb's law, which states that the electric field intensity equals k times the charge divided by the square of the distance. For our dipole, both positive and negative charges contribute to the electric field at point P. Let's calculate the distances from each charge to point P. If the distance from the center of the dipole to point P is r, then the distance r1 from the positive charge to point P is r minus a. The distance r2 from the negative charge to point P is r plus a. Now, we can calculate the electric field due to each charge. The electric field due to the positive charge at point P is given by E positive equals k times q divided by r1 squared. Similarly, the electric field due to the negative charge is E negative equals k times negative q divided by r2 squared. Note that both these fields are vectors and point in specific directions. To find the net electric field, we need to add these individual fields vectorially. On the axial line, the fields from positive and negative charges are along the same line but in opposite directions. So, we can simply add their magnitudes algebraically, accounting for the direction with the appropriate sign. The net electric field is E equals E positive plus E negative. Substituting the expressions for E positive and E negative, we get E equals k times q divided by r1 squared minus k times q divided by r2 squared. Now, let's substitute r1 equals r minus a and r2 equals r plus a into this equation. When algebraically simplifying this expression, we get E equals k q times the quantity 4ar divided by the quantity r squared minus a squared squared. In most cases, we're interested in the electric field at distances much larger than the dipole size, that is, when r is much greater than a. In this approximation, we can simplify further to get E equals 2 kp divided by r cubed, where p is the dipole moment q times 2a. Let's understand the physical significance of our result. The electric field due to a dipole at a point on the axial line. First, it's proportional to the dipole moment p. Second, it varies inversely with the cube of the distance, unlike a point charge where it varies inversely with the square of the distance. Third, the direction of the electric field is along the dipole moment vector for points on the positive side of the axis. To illustrate this inverse cube relationship, let's look at how the electric field intensity changes with distance from the dipole center. As you can see, the field decreases rapidly as we move away from the dipole. This is characteristic of dipole fields and distinguishes them from monopole, point charge, fields. To summarize what we've learned today, 1. An electric dipole consists of two equal and opposite charges separated by a small distance. 2. The electric field at a point on the axial line is given by the formula E equals 2 kp divided by r cubed for r much greater than a. 3. Unlike a point charge, the electric field of a dipole decreases as the inverse cube of the distance. 4. The direction of the electric field on the axial line aligns with the dipole moment vector. This understanding of dipole fields is fundamental in various applications, including molecular interactions, antenna theory, and the behavior of dielectric materials in electric fields.